Okay, if not, let me begin. Okay, so last time we calculated the delta T over T. So at T equal to T last scattering, the delta T over T was calculated to be minus 2 over 5 R at T star. And the fact that you are doing this calculation at T last scattering was not very important. What was important is that this is in the matter dominant area. Right? That's what he used. Right? We didn't use any particular property of the last scattering surface. So the first thing we'll try to study today is how is this related to delta T over T observed. Okay, because that's what we really want to compare with, because this is what we measured. And we'll do this by making some simplified assumption. And that assumption is that this perturbations psi and phi are time independent between TLS and T naught. Okay, and later we will discuss where this assumption fails and how to correct it. So let's suppose that we have our observer here. Okay, this is us. And this is a point on the last scattering surface. And the CMB photon comes from here, okay, and reaches us, but in general it can go along a curved path because the metric is not uniform, right? We are assuming that psi and phi are time independent, but in general they depend on x, right? Because that's what the fluctuations are supposed to be, right? In different parts of the universe, they have different values. So unlike what we studied earlier, okay, where we talked about the radiation coming from a faraway point reaching A, now we have the same situation except that this is traveling not in the background but in the background plus fluctuation. Okay, and the idea is that this can create new fluctuations even if the temperature was completely uniform on the last scattering surface. Okay, just by the fact that the psi and phi, okay, are not uniform, it could introduce additional fluctuations between coming from there to here. Okay, and you have to calculate that to make connection with what you observe. So this travels along a null geodesic. Travels along null geodesic. Okay, so the metric ds square, which was minus dt square 1 plus 2 phi plus lambda t square 1 minus 2 psi dx square. Okay, these are dependent on x but not on time. Right? So these in general can depend on x but not on time. That's our assumption. Yes.
So there we considered 5 to be 10.
Yeah, because we in the matter dominated era, phi settles down to a constant, right? Yeah, because of the super horizon thing in particular, right? But now we are talking about the traveling from there to us, right? It's going through a lot of things, right? And we are assuming that psi and phi, right, remain constant, time independent during this travel. I mean, in this region.
There is a horizon entry, then only there will be some time.
No, there are also other reasons, right? That time independence requires W equal to constant, right? But between then and now, the cosmological constant starts dominating, right? It's not pure matter anymore, right? So that will also introduce some additional time dependence, right? So these effects have to be taken into account, but those have to be done numerically, right? So I'm just making the simple assumption that there is no time dependence and see what result we get. Is this point clear? Right? So this assumption is not correct, right? Because you have to take into account time dependence to get the correct result, right? And the time dependence, as we discussed, comes from two sources. One is the super horizon, things which are super horizon here could become sub horizon with time, right? Because now we are talking about the not the last scattering surface, but beyond last scattering surface, right? Because phi and psi, okay, are much later. When the photon travels along this, right? That's at a much later time. And some of the modes which are super horizon earlier can become sub horizon, right? Because of this growth that we saw. So those have to be taken into account. Okay, but let's just assume that phi and psi are time independent and see what we get. Is this clear? Okay, so here, so we want to set this equal to 0. So this tells us that dt over lambda of t is equal to 1 minus psi of x minus phi of x Okay, so we are again working to first order in perturbation. So what we did was that I took dt over lambda t and this 1 plus 2 phi I took the inverse and it went to the other side, right? And then after you take the square root, it becomes 1 minus psi minus phi. Is it clear? Now let's try to do also something else. Let's suppose that we define a variable, I'll not call it tau, t tilde, define t tilde such that dt tilde is dt over lambda t. Okay, new definition of the time coordinate. Then the metric I can write as lambda t square times minus d tilde square times 1 minus 2 phi plus dx square times 1 plus 2 phi. Is it clear? Now, what one can show, okay, and this I will not prove, is that the null geodesics in this metric are the same as the null geodesic in the metric without this. Okay, so this is a conformal factor. This is what is called a conformal factor. It's an overall multiplicative factor. And what one can show is the null geodesics don't change under conformal transformation, right? So even if you make the metric multiply this by lambda t square, null geodesics remain the same, right? So you can, as far as null geodesics are concerned, we can pretend as if the photon is moving in this metric. Okay. And if you think of this metric, right, these are the time transitions metric, right? T tilde and T tilde plus constant give the same result. same metric, right? Which means that if we have suppose you have a null geodesics from A to B, we have found null geodesic by solving this equation. The same null geodesic, right, time translated, will also be a null geodesic. So if you start after some time from A, right, it will just follow the same geodesic, same path, right, except that everywhere the time will get delayed by the same amount. Is that clear? Okay, so this result I am going to use, right? That the null geodesics are independent of time, right? So you can just time translate the null geodesic. Okay, so the path remains the same. Path in the co-moving coordinates remain the same. So now let's go back to this equation. Right? I could have used the t tilde variable, but it doesn't really matter. Okay. So we suppose that we start a null geodesic starting at B at t equal to TLS reaches A at some time, say T naught. Then you have the equation integral TLS to T naught dp over lambda t is equal to integral d to a dx over dx times okay, this is along some path. Along some path C. We have to say, I mean, the path is needed, right? Because depending on the path, this integral can change. Right? This is a one-dimensional integral, but in a three-dimensional space, right? But some path that null geodesic is supposed to follow. Now we start at, let's suppose that a null geodesic starting at B at P equal to T LS plus delta T reaches A at P equal to T naught plus delta T naught. Okay. So then we apply the same formula again. So integral TLS plus delta T to T naught plus delta T naught dt over lambda T is integral A to B or B to A, it doesn't really matter because I'm taking mod. So this is along the same path. Right. So this is the result that I said, I stated, and this is the result I'm going to use, that the path doesn't change, right? Even if you start a little later, it will reach a little later. Okay, retaining the path. Now we subtract. So let's call this equation 1, that's equation 2. We subtract 2 from 1 or 1 from 2. Right hand side just cancel, right? Because it's the same integral, same part, same integral. So on the left hand side, we will get delta T naught over lambda T naught minus delta T lambda TLS equal to 0. Yes.
Because you pulled out that lambda.
Yes, but it's not trivial to show that the path doesn't change. You have to do some work. And it's not very lot of work, but it requires some work. Because the Christoffel symbol will still depend on this lambda T factor, right? So you have to do some work to check that the actual path doesn't depend on T.
What are we deriving? We're deriving cosmological redshift.
Yes, essentially you are deriving cosmological redshift, but in a background which is not uniform. Earlier you had derived cosmological redshift, but in a uniform background, right?
So uniform we mean FLRW.
FLRW, exactly, right? Now the metric depends on X, right? So that's why you have to re-derive it. Otherwise you could have used the earlier result. Right? So that's all we are doing. Okay? But at the end we get back the same as the earlier result, right? Because this side, even though it's complicated to calculate, it just cancels out when you take the difference. Okay, so this is that. So basically, we derived that we can use the formula for cosmological redshift, even though the background is not uniform in spatially. Right? As long as there's no time dependence, you can use cosmological redshift formula.
Both phi and psi are not time dependent.
Yes, we are assuming that phi and psi are not time dependent.
I see. So the dependence is there, but it factors out
Yeah, with lambda T, phi and psi are time independent, right? The time dependence just factors out like this. So by an appropriate conformal transformation, you can make this time independent, make the whole metric time independent, right? That's the statement. And then you are using the fact that the null geodesics do not depend on the conformal factor. Under a conformal transformation, null geodesics remain null geodesics.
But the kind of perturbations we'll be looking at are the perturbations of this sort, because didn't we let phi and psi usually depend on time?
Yeah, we did, but near the end of the matter dominated era, they all reached constants, if you remember, right? So that's what we are using, right? So for a while, phi and psi remain almost constant, right? As we discussed, that this is not strictly valid. This assumption is not strictly valid because eventually cosmological constant starts dominating. Right? So that part you have to take into account. So in that part, this assumption will not be valid. So you have to add corrections because of that fact, right? And similarly, this formula that we derived, right, the phi and psi go to constant in the matter dominated era, was for super horizon perturbation, right? And we are considering super horizon perturbation now, but a super horizon perturbation, right, could become sub horizon with time, right? So it is true that let's suppose that at the time of last scattering, these perturbations are super horizon, right? That's what we're considering. But as time goes on, right, those perturbations can also become sub horizon, right? And that will introduce additional time dependence.
So then this won't hold anymore.
Yeah, this won't hold anymore. We'll derive this formula making this approximation, but it's clear how to correct it, right? Because we know precisely how phi and psi depends on time, right? Because that while we cannot assume that phi and psi are time independent, right? We can calculate their precise time dependence, right? Because we know how to take into account mixed matter. The d mu has to change, right, in the Einstein's equation, and you have to take into account that k square term in the evolution.
But this calculation will modify how, because I'm not allowed to make phi or psi time dependent.
Yes, so that means there will be an extra term on the right hand side, right? That the time if phi and psi are time dependent, then there will be an additional contribution on the right hand side, right? It will not be zero anymore. It will be some non-zero thing, but that's calculable, right? What that non-zero object is, right? You have to basically calculate the path. Now, if it starts depending on the time, right, then you have to see how the path changes because of this time dependence, right? You have to take that into account and then calculate this difference, right? It will still be from B to A, but the paths will be different. Is that clear? So it's a calculable correction, right? That's all I want to emphasize. So first, let's just make this approximation and see what we get. Okay, so this gives us delta T naught. Lambda T naught is 1 by definition. So this is delta T over lambda TLS. Now, at the time of last scattering, if you look at delta tau, right? So tau is the proper, let's suppose tau is the proper time. So delta tau at the time of last scattering for a stationary radiation is given by 1 minus phi, sorry, 1 plus phi times delta T at the time of last scattering. Right? Because of this factor, the proper time will be multiplied by 1 plus phi. So then with this, I can write this as delta tau over lambda TLS times 1 minus phi. Okay, so the time interval that will be measured by the observer, right, delta T naught, is related to the proper time interval at the time of last scattering by this formula. Is that clear?
Which is the time that the observer will be observing?
Delta T naught, right? Difference between two successive signals. We are going to use it to see how the frequencies of light are scaled.
So this thing has a spatial difference because of phi.
Yes, indeed. This thing has space because phi is the fluctuation, right? You can use the space either the spatial variables or the Fourier transform, right? But indeed, this has space dependence, right? That's why there is a fluctuation.
But so this T naught is the time of the observer.
Yeah, that is ours.
But in general, you do not average over the observer. Yeah, the observer we just consider as
Us. Yeah, so you are not observed. So that's why at T naught lambda, there's no confusion. Lambda T naught is just 1. Right? All the fluctuations are in the sky at the time of last scattering. Right? So the fluctuation at the time of last scattering and possible fluctuation in going from the last scattering to us. Right? That's what we are trying to calculate. So this we can translate to a relation between the observed frequency of light to the proper frequency at the time of last scattering. So that will be given by lambda TLS 1 plus phi times nu proper at the time of last scattering. Okay. So nu proper basically means that it's the frequency measured in the proper frequency, right? It's 1 over the proper period of oscillation. Is this clear? So this allows us to relate the observed temperature to the temperature at the time of last scattering, right? To temperature at T. Okay. So T observed will be given by T at the time of last scattering. That's where it started. Lambda TLS times 1 plus phi. Is this clear? Okay, so let me repeat again. So if you are looking at some direction in the sky, say at B, okay, we receive radiation from there, CMB from there. The observed temperature that you will see is related to temperature at the time of last scattering, where it started, by this formula. Divided by temperature, yeah, somewhere something is wrong there. Yeah, T times lambda inverse, right? Yeah, because you are something went wrong here. The time difference, it will be red shifted. So it's okay, I think. Because lambda at last scattering was smaller, T at last scattering was higher. Right? So this product is the correct combination. Lambda T is remains constant. Lambda T remains constant, right? So if there's no fluctuation, then this is the correct formula. Right? T naught times lambda naught, which is 1, is TLS times lambda LS. Right? This is what this is the cosmological redshift formula that we had derived earlier. Right? Now we are taking into account the effect of the fluctuation. And what we see here is that the proper temperature fluctuation, so this I should also say proper. This is the temperature fluctuation that we calculated yesterday, last time. Right? Because we used the time variable, if you recall, when you calculated rho, right? We use a T lower 0, upper 0. Right? So that is the definition of rho in a coordinate system in which the coefficient of dt square is just 1. Right? We absorb that 1 plus 2 in the definition of dt square. So this we have calculated, right? So it's good. The fluctuation of this we have calculated. However, the fluctuation of this we have calculated at a fixed time slice. Right? We said that let's suppose we have some time t, right? Fix your time t, and the fluctuations are calculated on that surface. If that surface was not fixed, but imagine that there is the surface itself was wiggling, right? Because you don't know that in different directions in the sky, right? The last scattering happened at the same time. Right? In some direction, the last scattering may happen earlier. In some direction, the last scattering may happen later. Right? The surface may be wiggling. Right? In that case, there will be additional effects, because if the surface, say, if the last scattering happens a little later, right, the temperature would have fallen. Right? Just the average temperature would have fallen. Right? So that will induce an explicit fluctuation on the temperature, right, at the time of last scattering. So that is something you have to account for. Right? So in other words, this T last scattering may also fluctuate depending on the direction of the sky. Fortunately, the combination that appears here, right, this product is time independent, because T goes as 1 over lambda. Right? So suppose the last scattering surface was a little later, right, then T would have fallen, right, but lambda would have increased, right, keeping this product fixed. So using that, I can replace it by T proper at TLS bar, right, the average time times lambda TLS bar times 1 plus 5. That TLS bar is some average time, right? We don't really care very much, right, as to what the average time is. So this then allows us to calculate T observed over T bar observed. T bar is the average temperature. T bar is anything, some fixed time, right? I'm saying this is, let's say that this is the average time of last scattering, right? In different directions, last scattering happened at different time. Let's just take this average, right? The final result will not really depend on this T bar LS, right? We don't have to calculate what T bar LS is. So T bar observed is the average temperature coming from all directions in the sky. Okay, so let me write the expression for T bar observed, then I'll calculate the ratio. So T bar observed at T bar observed is given by T bar proper T bar ls times lambda of T bar ls. Because T bar by definition doesn't fluctuate, right? So that phi term will not be there. Is it clear? T bar is the average temperature. So using this, we can now calculate the ratio the T observed over T bar observed is given by T proper at T bar ls over T bar proper at T bar ls times 1 plus phi. Okay. This ratio is something that we had calculated last time. Okay? Because this is 1 plus delta T over T. Right? Remember the delta T over T that we calculated, right? Was at a fixed time slice. We said let's take a fixed time slice and we calculate the temperature variation in different places and divide by the average. Right? So here, because the argument has become T bar ls, okay, both in the numerator and denominator, that's exactly the calculation that I performed, right? At fixed time slice, that is T bar ls. Okay, and we calculated the fluctuations in T bar. So this is given by 1 plus delta T over T at the time of last scattering times 1 plus phi at the time of last scattering. Here it doesn't really matter if you take TLS or T bar ls because it's already first order, right? So the fluctuation in T will not change things very much. So this one, if you remember, I wrote down the formula. It was 1 minus, how much was it? 2/5. 2/5 R at T star. And phi at TLS also we had calculated. This was 3/5 R of T star. Okay, these are all in the matter dominated, right? If you look at the formula that we had, right, phi was calculated to be 3/5 R of T star. So we get this to be 1 plus 1/5 R of T star. So delta T over T observed according to this formula is 1/5 R of T star. Okay, so if you calculate the 2-point correlation function of delta T over T and delta T over T, you will calculate 1/25 of the 2-point function of R of T star with R of T star at the time of inflation. Okay? T star is basically the horizon exit. Right? So that's the way you make connection between what you observe and what happened during inflation. Is this point clear?
We have something like lambda t is constant, or lambda is this modified lambda 1 plus phi.
Lambda T equal to constant. Okay.
Lambda t is a constant. That's the thing that.
No, lambda T is not constant, right?
Lambda is the temperature.
Yeah, lambda times the temperature. Yes, indeed. Right.
So when we write the P observe in the observed metric also, like in our current time also the same fluctuation. Why that 1 plus phi is not cancelling out?
Oh, because that phi was, I mean, the phi at a particular comoving coordinate at the time of B, at B, right? The phi that is relevant for us will be phi at R equal to 0, right? But that is the one, that is the same, right? That is not changing, right? Certainly during the observation, it's not changing, right? So you can just absorb it. I mean, you can just declare that phi is 0,
Oh, okay.
right? it makes no difference because you are calculating delta t over t, right? So that phi is going to affect delta t and t in the same way.
It's like a reference point.
Exactly, that's like a reference point, right? So the point is that the phi actually changes as we discussed, right? As it travels, right? Phi is different in different regions of space because what you are studying earlier is at a fixed co-moving point, what the fluctuation is, right? Or its Fourier transform, right? So this phi is not the same as that phi.
What's the difference between T proper evaluate the average last scattering time and T bar proper?
Yeah, T bar proper is the average over angles, right? T proper is the value at T at a particular angle.
Okay.
Right? So bar will denote always averaging over all angles.
Okay. Then this will be the T tilde.
Exactly.
Small t bar last scattering, that is also angular average.
That's also angular average indeed. Right? But the small t bar at last scattering is not particularly important because you can take it to be any time that you like in that area, right? Matter dominant area.
That's because you are saying that T proper and lambda are like sort of cancelled.
Exactly, right? That any error in TLS that comes from uncertainty in TLS cancels against this. Right? So this combination is unchanged. Right? Otherwise, it has to you have to do more work, right? Otherwise, you have to figure out in different directions, right? How the last scattering time changes, right? Because in general, you can imagine that if at some point the temperature is a little higher, right? The last scattering will take place later. Because why does last scattering happen, right? As the universe is cooling, right? You saw that at some point, right, it becomes more efficient for the electrons to get bound to protons, right? And that stops scattering. Right? Now, if in some region the temperature is a little higher, then there the electrons are more likely to be kicked out of the proton, right, of the hydrogen atom. So the last scattering will happen later, right, when the temperature cools sufficiently. So this, because this combination appears in this way, right, that part of the calculation is saved, right? You don't have to worry about that part of the calculation, that when exactly the last scattering takes place. Is this point clear? So in general,
Isn't that the same fluctuation we had plus minus 253 Kelvin?
yes, indeed. So that fluctuation was plus minus 253 degree Kelvin, but that plus minus was not a fluctuation. Okay, that plus minus came because it depends on when what you define as a last scattering surface, right? The opacity starts increasing, right, and we had this peak, right, and the width of the peak will define as the last as this 253, right? So that 253 are not a result of the fluctuation, right? We had taken completely uniform background, right, and this 253 was exactly when you define it to be the last scattering, right, when the opacity is at the peak or half of the peak or twice the peak and so on, right? So that's the error that this 253.
This is different.
This is different. These are different angles, right? Can have different scattering, right? This is much lower because it is 1 in 10 to the 5 fluctuation, right?
Oh yeah. Okay. So after choosing one scattering surface.
Exactly. Let's imagine that we define exactly the location of the peak, right, as the time of last scattering. Right? Then you are talking about the fluctuation in that peak in different directions. Right? Then this 253 is no longer there, right? Because you have made the zero width by defining that it to be location of the peak, and now you are talking about the fluctuation of the peak itself. Is this clear? Right? So it certainly saves a lot of work that you don't have to calculate TLS exactly. Any question? Okay. Now, as we have already discussed, right, this approximation is not correct, right? It fails. It fails due to two reasons. One, because at late time, it's not matter dominated anymore, right? Matter and cosmological constant starts mixing, right? So the equation of state that we had used, P equal to W rho, has to be changed, right? But we know how to change it, right? We know exactly what the equations are, right? We just have to take into account the fact that now it's a mixture of two systems. One part of it is matter, part of it is cosmological constant, and then evolve the equations, right? The other effect is that depending on what the value of K that you are looking at, here I use a position space picture, but all these calculations are actually easily done in the momentum space, right? Which you can go back and forth, of course, right? To visualize, it's good to use keep the position space picture, but for actual calculation, it's always good to use the momentum space picture, right? So you work in a Fourier space, and there, depending on the value of K that you look at, the modes can become sub-horizon with time, right? And once it becomes sub-horizon, then it starts this oscillation, right? So that also has to be taken into account, right? So in actual practice, phi and psi are not time independent, right? They do depend on time, and as a result, the path of the null geodesic also depends on time, right? But we know how to take that into account, right? Because it's just classical GR, right? You just have to do a little more work to figure out how the null geodesics are changed. Okay, so you have to take into account that in this integral, right? So the right hand side now will no longer be 0, but there will be some corrections. Okay, so as far as results are concerned, this is all that I'll discuss, right? I'm not going to derive any more new result. Okay. But the last topic that I want to discuss is a different way of doing the same calculation that we did. Okay, and I'll try to motivate why we want to do this, right? Why we want to use a different method to do this calculation. And the part of the calculation that we'll repeat, okay, is the part where you evolve from the radiation dominated to the matter dominated era, right? Remember the delta T over T we calculated using in a radiation dominated era, right? We calculated delta rho over rho and computed delta T over T from there, and then we evolved it to get the matter dominated result by solving the differential equations that we had written down. But those differential equations that we had written down, right, for time evolution of phi and psi, etc., those assume a specific form of the energy momentum tensor, right? Those assume that the energy momentum tensor has this perfect fluid form, right, where it's like a locally you have a system in thermal equilibrium, right? It's just that that system, the temperature can vary from place to place, and the fluid itself can move from place to place, right? In each point there is a local velocity, right, which can vary continuously. So that is the picture that we used for the energy momentum tensor, and this is expected to be a good picture as long as the system is in local thermal equilibrium. But you know that between matter dominated era and radiation dominated era, between radiation dominated era and matter dominated era, the photons went out of thermal equilibrium, right? So you can no longer assume that we have a system in thermal equilibrium, local thermal equilibrium, and use the corresponding form of the energy momentum tensor. Is this? Yeah. So we assume that, okay, the equations that we had written down assume that the energy momentum tensor is given by this perfect fluid, right, where in each small region you have a system in thermal equilibrium, right, but the temperature varies from place to place, and that system has a local velocity as a whole, which can also vary from place to place, right? This assumption fails once the photon goes out of thermal equilibrium, because between the matter dominated era and radiation dominated era, right, photons go out of thermal equilibrium. That we had seen, right, in the when you are doing even the standard FRW cosmology, right? Between matter dominated era and radiation dominated era, the interaction between photons and electrons become low, right? And there is not enough scattering of the photons to keep them in thermal equilibrium. And once we know that they are not kept in thermal equilibrium, then we cannot use the formula that we had written, right, which was based on the fact that you have a local fluid in thermal equilibrium. Is that clear? Now, we expect that this fact will not affect the super horizon perturbations. Why not? Because we had argued that for the super horizon perturbations, right, any microscopic interaction is irrelevant, because anything that happens microscopically, right, that can only proceed up to horizon size. Right? If the length scale that you're talking about is larger than the horizon size, right, then those local fluctuations is not going to affect the average over long distances. Right? Whether the photons have local thermal interaction or not, right, is irrelevant if you are doing average rate. If you are, for example, looking at the average densities over large distance, right? Because the only difference will be whether the photons are here or there, right? Because the photons, once they carry certain energy, they have to be there, right? Whether they are in thermal equilibrium or not depends on whether the photons are scattering a lot and being confined in some small region, or whether they are free flowing from one region to another region. But as long as that free flow doesn't exceed the omega inverse, or the omega inverse, right, or 1 over k, it doesn't matter because you're doing average over that large scale, right? So this local flow is not going to affect those averages. Okay. So we do expect that for super horizon perturbations that we have used, right, this feature is irrelevant, right? The fact that the system goes out of thermal equilibrium locally should be irrelevant. But the method that we used, right, even in principle cannot be used for sub-horizon perturbation, right? Because for sub-horizon perturbation, this is not true, right? You cannot use local thermal equilibrium. So what you are going to do, right, in the rest of this course, which maybe it will finish today or maybe half an hour tomorrow at most, okay, is that we will redo the calculation, okay, taking this into account, right, that the system is not in local thermal equilibrium. We'll apply it only for super horizon perturbations, right, not sub horizon perturbation, but the equations will be written, right? So there will be additional terms that you have to write for sub horizon perturbation, but at least we will set up the equations, right, which can be corrected for sub horizon perturbations, and then we'll verify that for super horizon perturbations it reproduces the result that we got. Right? That's a consistency check, because those results we got by using a wrong method, but we argued that those wrong methods are correct as far as super horizon perturbation is concerned. Is this point clear? Okay. So we are now going to not assume local thermal equilibrium and see how we can proceed. So now instead of talking about a thermal fluid, we are going to talk about photons. Okay, we assume that there are photons filling the universe and there is some phase space distribution. Okay. So let's suppose that delta V is a small phase space volume for the photons. And F times delta T, this depends on, of course, the phase space coordinates, depends on phase space coordinates, which are x and p, right? The position of the photon and the momentum of the photon. This is the number of photons in volume delta T. So then you know that if in thermal equilibrium, F can be written as this, correct? 1 over exponential E over T minus 1, where E is the proper energy of the photon. I'll write down the formula, and T is the local temperature. So E is basically square root of minus G naught naught, G naught squared, which for us will be 1 plus phi times G naught, because G naught naught is minus 1 plus 2 phi. Okay, so this scaling is needed because you want to go to the proper time, right? Because the temperature that we had introduced was the proper temperature. If you recall, we scale the time variable to make the metric coefficient dt square and then define the temperature in that time, right? It is using that time coordinate. So what is the strategy? So this, to begin with, right, the system was in thermal equilibrium. So this is the initial condition. We start with this F, and then we simply evolve it as a function of time. Yes, yes. But this G00 is the G00 before the rescaling, right? So that's why its P0 will be measured in the original coordinate frame, right? And so you have to multiply by this 1 plus 5. Right? The new G00 will be basically this G00 times the scale time will have to be scaled to get the proper time where this is set equal to 1. Okay. So we are going to now calculate the time evolution of F. So the picture that we have is that we have a bunch of photons in this phase space volume. The phase space volume, with time, the photons are moving, right? So the phase space volume will go somewhere else. It may change its shape. There are these photons over here. So here it's F at T. It will be F of T plus say dt. So F times delta V at T should be equal to F of T plus delta T, T plus dt, delta V at T plus dt. But by Liouville's theorem, this is the same as delta V of T. If you remember, the phase space volume doesn't change with time. Okay, so this is Liouville's theorem. So we see that F of T should be equal to F of T plus dt. This can be translated to a differential equation, d dt of F of T equal to 0. But d dt here refers to the derivative along the trajectory, right? Because d dt gets contribution from two sources. One is that even if you are sitting at the same point, right, time evolution will change F, right? Some other photons are entering this, right? So time evolution will change F. But there is also a change because the actual volume is moving, right? The photons are not remaining free, right? They are moving with in this metric. So that has to be taken into account. So this we can write as the partial derivative of F plus where q alpha are the coordinates of a space. Which can be written as f, x, and p. And f in general is a function of p as well as q, p, x, and p. In equilibrium, it depended only on the energy, right? The P0. But when it's out of equilibrium, we don't know, right? So you have to allow for dependence on all the coordinates of the phase space. Is it clear?
It should be dependent on momentum also.
Yes. So F depends on x and p.
So partial derivative is the moment.
Yeah. So this q alpha stands for both x and p, right? So alpha runs from 1 to 6. Where did I write it somewhere? No. Yeah. Q alpha are the coordinates of phase space x and p. Right? So alpha runs from 1 to 6. So the idea is that we will try to use this differential equation to evolve f, right, and see what we get at the end. And what we'll try to do is to reinterpret the final f that we get as a thermal distribution, even though the actual evolution is not, it's not in thermal equilibrium, right? But if we can somehow fit the final f into this form, we can use it to define a local temperature. Is that clear? Yeah. So we start with this f and we evolve it by this equation, right? Suppose at the end of the evolution, right, we find that the f that we get can be written in this form with some t and some e is the energy of the photons, right? Suppose it can be written in this form.
Yeah, and the map from E to P is one to one. The given some E.
Yes, E is just this. E is this P0, right? E is this. This is E.
But there's also some metric dependence. Phi.
Indeed. So phi depends on the position of the where you are calculating this. So of course everything will depend on phi.
Okay, that's already given. Okay.
Yeah, phi is given to you, right? Phi is not something that you are allowing. I mean that evolution you already know. Is it okay?
So what were you saying that after evolution we can write it in this form?
Suppose we can, right? I'm not saying that we can, right? If we can write it in this form, right, then we can reinterpret that T as a local temperature after evolution. And it may happen, right? Just like, I mean, even in the case of uniform background, right, without the fluctuation, we saw that even though the photons decouple, right, later on we can reinterpret the photon gas as a thermal gas, right? Because every frequency gets shifted in the same scale by the same scale, right? So something like that may happen, right? We don't know if it will happen or not, but we have to keep that in mind, right? If it doesn't happen, then that means that the final state cannot be interpreted as thermal gas anyway. So let me write this equation more explicitly. So del F del T Okay, this is the equation that we are trying to solve. Okay. So to solve this, you have to first find the photon trajectories. Right? You have to know these, right, in the geometry that you are given. Okay, once you know the find the expressions for these, we can substitute here and try to solve for del f for f. So the photon trajectory, of course, is given by okay, where sigma is some affine parameter. For massive particle, normally we choose sigma so that it's the proper time. Okay, so for the photon, of course, we cannot choose that, right? Because proper time along the photon trajectory is 0. Okay. So what we will do for the photon is that we scale sigma, we choose sigma such that let me put upper index here. It's P naught. Okay, now P naught hasn't, of course, hasn't appeared in this variable. P naught is the energy, that's a derived variable. So let's try to see what P naught is. So we use the fact that G mu nu, P mu P nu is 0. So this tells us that 1 plus 2 phi P0 square minus 1 minus 2 psi P square lambda T square 0. This is RE. In any case, so P0 we get as from here is 1 minus phi minus psi times mod P times lambda T. So we'll try to use the variable E rather than P0. Okay, but let me write down the next equation anyway. dP0 d sigma. This requires, oh, so maybe I should write this equation slightly differently. So we define P mu. We define P mu dx mu d sigma. So maybe I should say P mu, this is a relation, right? Once we have chosen P0 as dx0 d sigma, then Pi will be dxi d sigma. So this. So this equation can be written as d P mu d sigma plus gamma mu nu rho d mu p rho equal to 0. So this is one set of equations, and then dx mu. So this is another set. These are two sets of equations. Okay, that we have in relativistic form. but it's actually really 6 equations, not 8 as it would suggest, right? Because of this condition that P0 is not an independent variable. Okay, and x0 by definition is a time. So here I'm going to write down the equation for P0, okay, which I'm not going to derive. dP0 d sigma is given by 1 minus 2 phi e square times minus phi dot minus 2 we have kept up to first order term. And dx0 d sigma we have already written as P0 times is P0, which is P0 was E times 1 minus phi. So you are going to divide this by this to calculate the time derivative of P0. Is it clear? Because this is deep. Sigma is just an additional affine variable, right? We want to get rid of sigma, right? Because we want to write everything in terms of the time, right? Time derivative. So you can take the ratio of these two, right? So this is say 1 and 2. So you take 1 by 2. Okay, so I'm not going to do this in very much detail because this is the standard solving particle trajectory in background. So dP0 dt we get as 1 over P0 times dP0 d sigma, which is E times 1 minus phi times minus phi dot minus 2 okay, I have to define this p hat I. I'll do it in a minute. So p hat I is just a unit vector along okay, the unit vector along the vector along the moment. And we take E p hat I x as independent phase space coordinates. Okay, it's completely up to us as to how we parameterize the phase space, right? We choose to do it by not the 3 vectors p, right? But by this unit vector p hat along the vector p and E, which is a rescaled energy, right? Which, as you saw, is related to, because of this fact, right? The mod p, you can see that P0 is related to mod p, so E is also related to mod p. Okay, so instead of taking the 3 components of p, we are taking the unit vector along p and this variable E. Is it clear? So we can think of this as an equation for E. And it turns out that that's basically what we'll need. We don't need very much more, at least for this part of the calculation. So this gives you a d dt of E times E0 was E times 1 minus phi, right? E times 1 minus phi is equal to this. Is it clear? This is just the motion of a particle, of a photon in this background. That's all you are calculating, right? And this particular equation tells us how the energy of the photon is going to change as it moves. Yeah, there are similar other equations which will tell us how the momentum changes as it moves and so on. Okay, but as I said, we don't need this right now. The other thing you would notice is that I have taken the photon equations which are free. Right? I'm assuming that the photons are freely moving. Okay? That's in fact the other extreme case compared to thermal equilibrium. In thermal equilibrium, the photons have a lot of collisions. Right? Here you are assuming that the photons are completely free. The actual situation is somewhere in between. Right? Because there are electrons and protons floating around, and the photons do collide with them once in a while. So the complete calculation will require setting up a similar phase space density for the electrons and protons, etc. And then using the density and knowing the cross section of the scattering of photons from those, right, we can set up the equation so that you also take into account the effect of collisions. Right? The photons will not be just freely flowing, right, but they will scatter from the electron and go in some angles. Right? Those you can calculate if you know the phase space density of the photon as well as the electron and proton. You can calculate those from known cross section. Right? So those in actual calculation, all those have to go in. Okay? But since our goal is to try to reproduce the super horizon result, right? Just show that this method works in the same way. Right? For us, we can just ignore this fact. Right? But if you want to actually study sub-horizon evolution, you have to take those into account. Because these collisions, what does it do? Right? It just changes the direction of the photon. Right? But it cannot change anything if we average over long distances. Right? It will transfer some photon momentum from one to the other, right? Some electron momentum from one to the other. But the averages over long distances, right, will not be affected by this. Right? That's the reason for super horizon perturbations, we expect that this shouldn't matter. Right? It's the same argument that we gave, that the microscopic physics shouldn't affect the super horizon perturbation, right? And whether the photons collide with the electrons or not, right, what the cross section is based on microscopic physics. Right? And so those shouldn't affect the super horizon perturbations. Right? That's because you are doing averaging over long distances, right? So if something flows from one region to another region, right, average over long distances will not be affected.
What is the evolution of energy we are concerned from from the last scattering to today, or is it from?
No, this is from last scattering. This is not from last scattering to today. This is from the radiation dominated era to the matter dominated era. That is the part of the calculation you are doing.
Okay. In between the photons go out of equilibrium, and this electron proton they will be in thermal equilibrium with the photon.
Exactly. Right. So electron and proton will be in a thermal equilibrium. Okay. thermal gas, but the photons are not in thermal equilibrium. Okay, so the other thing we have to calculate is d phi dt. So d dt, remember, is motion along the trajectory, right? This is also calculating how things change as the photon is moving. D phi dt is given by del phi del t plus right, because phi depends on the position in general. So d phi dt is given by this. So as the electron is moving, as the photon is moving, the phi, there's an intrinsic change in phi, but there's also a change because just the photon has moved to a different place. So this I can write as phi dot. This is what we had called phi dot, right? Sitting at a given point, seeing how it varies. And this one is times pi. Sorry, this is not pi, this is pi over p naught probably. Because you're calculating dxi dt, right? dxi d sigma would have been pi, but dxi dt will be pi over p naught, and p naught again is related to e. P naught is e times 1 minus phi. So now we are going to substitute this in the equation for f. So we use
We start with T vector and T vector. Why do we need an extra degree?
oh, because mod p we have eliminated. Mod p is not a variable anymore.
Oh.
Right? We have just the p vector. We have traded in for the unit vector along p and e. Right? So we have not changed the number of variables. We just use different set of variables, and this combination, when you write del f del q alpha dq alpha dt, right? That's invariant under change of variables. Right? Doesn't matter what q alpha you use, right? As long as you use the same q alpha for dq alpha dt and del f del q alpha is the same. Yeah, so that's why we are allowed to choose anything that you like. Is this clear? So now we are going to go to momentum space and use this super horizon nature of the point. Momentum space plus assumption of super horizon perturbation. And see if we can simplify things. In momentum space, this quantity basically becomes I ki phi, right? And super horizon basically means that you ignore all k's. Right? K goes to 0 is the super horizon limit. So this is equal, this we can set equal to 0, right? For super horizon perturbation. Basically, whenever k appears, you can make that combination, right? I mean, because by dimensional argument, you can argue that whenever there is a k that is appearing, right, effectively is that k over lambda is that comes in. So whenever, so the general rule is that whenever you find a k, you can set it equal to 0. Similarly, here there is a k in the momentum space, right? Then again, this you can set equal to 0. This has a ki and set equal to 0. This term is gone. This term we can argue is second order in perturbation. Okay, let's see why. So f was the distribution, phase space distribution function, right? In the absence of perturbation, right, there is homogeneous and isotropic, right? So f couldn't depend on p hat, the direction of p, right? F can only depend on the magnitude. So this is already first order in perturbation. dp hat I dt, right? In FRW, right, we had seen that the direction doesn't change, right? The straight lines are null geodesics, right? So in order for dp hat I dp dt to be non-zero, you need a perturbation, right? So then this product is second order, right? So this is second order, and this also you can set equal to 0. Is this point clear? Right? So some things are set equal to 0 because it's a super horizon, and anything that has an x derivative we are setting equal to 0 because it's super horizon, and some things are being set equal to 0 because it's second order, right? In the homogeneous isotropic universe, both terms vanish. So this now makes things simple, because now we can, and this also, but this also is set equal to 0, right?
Why was the first term perturbation justified as the it will depend on the magnitude of
the first term, f, yes, because in a homogeneous and isotropic universe, if you have local thermal equilibrium, right? There you know that the photon distribution function only depends on the magnitude of the photon, right, or the photon momentum. It's just a thermal gas, right? The direction doesn't matter, right? Because the gas is anisotropic, it is actually not 0, but it's proportional to the perturbation. Right? Anisotropy has to come from the perturbation itself.
Oh, right.
Right? If there's no perturbation, then there'll be no anisotropy in the distribution function. No, for this it's different, right? This is dp hat I dt, right? This says that what is the rate at which the direction is changing, right? And in homogeneous isotropic universe, dp hat I dt is 0, right? P hat I is not 0. That kind of course, photon carrying momentum in some direction, but it keeps going in a straight line, right? In the coordinate system that I have used. So that's the reason why this term is also proportional to perturbation. Okay. So now we are more or less in business, right? So the first equation, let's look at the two equations. First tells us that E dot okay, first gives you d dt times 1 minus phi plus E times minus phi dot. Right here, I use the second equation because d phi dt had two terms, but this term I set equal to 0. Right, so that's a E times minus phi dot. This is equal to E times 1 minus phi times minus phi dot plus psi dot minus h. Okay, some terms cancel, as you can see. Already minus this E phi dot is common. And this equation now tells us that this is 0, so plus because these terms have been set equal to 0. Okay. And now the idea that you take d dt from this equation and substitute, right, to get an equation just for f. Is that clear? Right. So substitute for d eta. So use 1, we call this 1 and 2. Use 1 to substitute d dt into. Okay, and I'm going to just write the answer because it's a straightforward algebra. And you always keep up to first order in perturbation. So we get is this clear? So this allows us to start from a given initial condition on F, okay, which is thermal distribution, and evolve it. Right? It's a first order differential equation. Right? So if we knew F at an initial time, you could just evolve it to get F at any later time. Okay? And now I'm going to write an ansatz for the solution. Right? Whether the ansatz is correct or not will depend on whether you can actually solve it. If you can solve the equation with the correct boundary condition, then you know that you have the solution. Right? Because the solution is unique once the boundary condition is satisfied. So now we are going to try. Oh, maybe I should just write one more equation. Multiply by f to the minus 2. So we get et of f to the minus 2, sorry, f inverse. Okay, because both of these just gives a minus sign, right? F to the minus f to the minus 2. So try now f as 1 over exponential okay, you are going to try to fit it in a thermal distribution, right? With temperature given by T bar times 1 plus theta and see if we succeed. That imagine that we can solve this, right? Then we know that theta, the initial condition on theta was delta T over T in the radiation domain, right? We could just start from there and evolve, right? Because it certainly satisfies the boundary condition that we have, right? By setting theta to be what theta was in the radiation domain. Theta is delta T over T. So you are going to now substitute this and try to solve it, right? So this gives you plus So let's do this. So you get E over T bar 1 plus theta. So E is not, E is just a variable. This E is an argument of F. F so F of E hat I X is what we are calculating, right? Okay. So you take the del T of this, right? We are not going to vary this E, right? The variation with respect to the parameters that we have, because E's are the independent variables of F. So this gives you minus T bar 1 over T bar square I think I'll just finish in another 2-3 minutes. Yeah, so 1 by T bar to 1 plus theta. Oh yeah, thank you. Yeah. Yeah, it is also 1 plus theta. Thank you. Because I have already taken out this part. So this, so T bar times 1 plus theta just gets cancelled. Is gone. One by T bar, del T bar del T. Right? This cancels this EH term. There is an E missing somewhere. What did I think there should be an E here, right? Because you are taking the derivative, so E was in the exponent. So when you take the derivative, E is also coming as a factor, right? So 1 over T bar del T is basically minus H, right? Because T bar lambda is constant, right? So T bar dot over T is minus lambda dot over lambda. So this cancels this. So this one, let me write. Right, so this one cancels this one. So we get pardon? Minus delta, yes, thank you. Minus delta by delta. Okay. In this 1 plus theta, I can replace by 1 because theta is already a perturbation, right? So theta times 1 plus theta will be second order. So we get E theta dot minus E theta dot plus E psi dot equal to 0. Right? So theta equal to psi plus constant. So this is a solution. We have found a solution for theta, right? And that means, and now we have to set the initial condition to theta to be whatever it was during radiation dominant theta. So this constant is fixed by requiring the theta in radiation dominated era is what you had gotten for delta T over T at the radiation dominated era. And that was, I think, minus 1/3 or. Okay, it doesn't matter. I'll write the formula. Let's call this theta r. So we get theta m minus psi m equal to theta r minus psi r. Right? These are matter dominated results. These are radiation dominated results. Okay. So theta m that this is what we are interested in, right? Theta m is delta T over T in the last scattering, matter dominated era. This is psi m plus theta r minus psi r. And this is exactly the formula we had found earlier. If you remember, right? Theta r was delta T over T in the radiation dominated era. Okay, so let's write the formula explicitly. So theta so delta T over T at the radiation dominated era, this was given by minus 1/3 r. Psi m is 3/5 r and psi r was 2/3 r. Because these are all that we had calculated earlier. So this gives you 3/5 r plus minus 1/3 r minus 2/3 r, which is minus 2/5 r. Okay, in fact, we didn't even have to do this calculation. This is exactly the result we had found, right? But more importantly, this is the result we had found earlier by using the fact that you just use a redshift formula, right? Pretend that as if it's just normal radiation, and we use a redshift formula to get this formula. Okay. So what we are saying here is that using this transport equation, right, which is telling us that how the phase space density changes as a function of time, okay, we arrive at the same formula, right? And it's not surprising because we argued that at least for super horizon perturbation, we should get the same formula. Okay. But the advantage of setting up the calculation this way is that now we know how to take into account the corrections for sub horizon perturbation, right? We cannot ignore those ki's anymore, right? And we cannot ignore the collision anymore, right? So this is the way the actual calculation is done, right? For sub horizon perturbation, how to evolve from the radiation dominated era to the matter dominated era. Is this clear? Okay, so this calculation you probably should do it on your own because mostly it's just solving photon equation in the background. Okay? That's all we did in this analysis, and that's what led to this final result. Okay, so I think that's the end of the course. Right now, it's up to you to submit your assignment and give the talks. Right, my job is over. And if you have any questions, just feel free to drop by, or if you don't find me, just send an email, right, so that we can fix some time for discussion. Photo, okay. But who will take photo? Yeah, we can all stand in front of the camera as long as you take off. Okay, I think let Asif come back.
I can take a screenshot.
All stand. I think Asif has gone to call someone.
Ashoke was the first.
No, we cannot all.